Hello, everyone, and thank you, Anna, for the kind introduction. Today, it's a great pleasure to be here, and I'm Sindhu. I'll be presenting our work today on gesture synchronization. So this is a work with my advisor, Professor Andrew Zisserman from University of Oxford, and I'm a second year PhD student at Oxford from Visual Geometry Group, VGG. Okay, let's get started. That's fine. Yeah, let's get started. So today, first, let us begin by, I'll give a very high level overview of what we are trying to do in this research and how we are trying to achieve our goals. So basically, one of the major key ideas here in our research is to develop AI systems which are capable of understanding human communications through the analysis of videos which are focused on a human interaction. Now, in this, there are multiple aspects. The first one is speech. So, speech delivers the linguistic content of what is being spoken. Then, it also involves understanding the facial expressions. So, expressions will tell us about the intent and the tone of speech. Uh, the same sentence can be uttered with multiple different emotions or expressions, and they will have completely different meanings. And finally, it also involves the understanding of body language or gestures, which are basically arm and hand movements that we all spontaneously emit when we speak. So these gestures provide the non-verbal information, and this helps the listeners to comprehend what is being spoken. Now, our research falls into this category of research where we are trying to enhance the AI model's capabilities to understand and comprehend human communication through various forms of these gestures. So, okay, this was a brief highlight of our objectives and research goals that we are trying to achieve in this work. Now, let us start with a very simple question. So, I'll be showing a few videos here, and the question and the task for all of you is to try to identify who is speaking in these videos. Here is the first example.
It's the beginning of December. So yeah, very clever machine. This is one of our.
Here is another example.
Like the poor man's version of Ryan Reynolds.
And here is one more.
And then I went back, and while I was at home.
Okay, so the answer to the question is yes. For us as humans, this is a pretty straightforward task to identify the active speaker in these videos. Now, in computer vision literature, this task is known as active speaker detection. Basically, when there are multiple speakers in a scene, we want to determine who is the active speaker. And traditionally, the current works today rely on signals from lip synchronization to determine who is the active speaker. Basically, if there are multiple people in a scene, then the lip movements of each speaker is matched with the speech to find out the speakers whose speakers lips aligns the most with the spoken words, and this way we can identify the active speaker in a multi-speaker scenario. However, if we carefully observe the videos here, then we can clearly see that none of these videos have faces or lip movements visible in them. But then there is one other signal which is very common and probably which we all of us used to identify the active speaker, and that is body language, body movements, or gestures. And that is exactly the focus of our work today, where we want to identify and analyze if there is a natural correlation that exists between speech and gestures, and then use these signals to identify the active speaker. So basically, we do not want to rely on faces or lip movements, but rather rely on gestures and find out the correlation between speech and gestures, and then try to use this signal to find out the active speaker. So we propose a new task in this work, the task of gesture synchronization, basically to determine if a person's gestures are correlated with their speech or not. The objective here is to analyze to what extent it is possible to answer the question, who is speaking, from gestures alone without the need of a talking face or a talking head to be available. So before we dig into understanding the correlation between gestures and speech, let us first look into the correlation between lip movements and speech, which is popularly known as lip synchronization. Basically, lip synchronization is the process of matching the speaker's lip movements with his or her speech segments. Let us see some examples here.
It's like all of my life, everyone has always told me, you're a shoe.
So in this video, the audio and the video are perfectly in sync. Now we will see another example where if you observe the lips, you can clearly see that the audio and the video are out of sync.
My life, everyone has always told me, you're a shoe.
I hope it was visible, especially for the Zoom viewers. And the audio is also audible, right?
The audio is audible, yes.
Right.
Yes, okay, thank you. So I'll play the video again. And here it's very clearly noticeable that the audio and the video is completely out of sync. Let's see the video again.
My life, everyone has always told me, you're a shoe.
So yeah, this is the process of lip synchronization. And it is very common for humans to notice these lip sync errors very easily. Now, in TV and film production, this audio to video synchronization is a routine task because audio and video are usually captured using different equipments. So lip synchronization becomes very crucial, automatically identifying whether the audio and video are in sync. And if they are not, identifying and correcting these lip sync errors has become very important. And thus, this lip synchronization is a widely researched topic. And today, there are multiple existing systems which work really well, which are capable of determining whether the video and audio are in sync using lip synchronization and also correcting these lip sync errors. Now, we know what lip synchronization is. So let us move forward and understand some of the existing works of lip synchronization and simultaneously also look at the challenges of using them in real world scenarios. As I was explaining previously, this lip synchronization is a widely researched topic and has been solved in prior works. This is a very, very strong signal because lip movements and speech are dense in time and they are casually related. Let us see one example here.
Sorry, it didn't fly. Sorry, it didn't fly.
Rocket and Matt wanted to know if anyone had 5 litres of bleach. Rocket and Matt wanted to know if anyone had 5 litres of bleach.
So here, the videos on the right-hand side indicate the sound source. And these are basically the lip movements of the active speaker. Thus, if we can find out the lip movements of the active speaker, we can easily use these signals as an indication to determine who is speaking in these scenarios. But then the question arises as to what happens if the face or specifically the lip movements are not visible. And there could be multiple such scenarios where the faces are not accessible. For example, if the person is speaking from a distance and lips are too small, or scenes in movies where there are lots of pose, camera angle, and scene changes. One such example where lips are occluded is shown in this example here. And we also saw some of the examples at the beginning of the presentation. So now, in all these scenarios, it is very clear that just solely relying on lip synchronization will not be applicable and it will not work in all these cases. Thus, our proposal is to determine who is speaking from gestures alone without any need of the talking face or the video to be available as input. So just to recap, I think we all are clear of what task we are trying to do here. It is the task of gesture synchronization to determine and find out if the gestures and the speech are in sync or not. And then if they are in sync, then we can easily determine who is speaking in a multi-speaker scenario without the need of a face to be available. All right. So let us now see how we approach this problem. Here is a brief overview at a very high level of what is happening in our method. Basically, there are these three major blocks or modules that are involved in our method. We have two streams of input with us. One is the video input and the other is the audio input. Now for the video input, we have a video encoder, which is basically taking these video signals, it processes them and generates the output video embeddings. Now, similarly, for the speech side, we have a speech encoder, which takes in the speech signal as input, processes these signals, and generates the speech embeddings as outputs. We now have two sets of embeddings with us. One is the video embeddings, and the other is the speech embeddings. The task here is to match these embeddings to determine if they are in sync or out of sync. So if the audio and the video are in sync, then these embeddings will be close to each other. And on the other hand, if they are out of sync, then they will be far apart. So this is how we design our system using these three major blocks: video encoder, speech encoder, and then the synchronization module. So before we begin looking into the details of these three major modules involved, let us first try to understand how do we even get the data to train such a system and how do we formulate this problem. So once we have the speech and the audio embeddings with us, we want to make the model to learn the synchronization between the gesture input and the speech input. To do so, we create synthetic data. Let us see how do we do that. So consider a sequence of frames and the corresponding audio signal. Now, a subset of these frames and its corresponding audio is randomly selected. This forms the positive pair because audio and video are in sync. Now, the same subset of frames is selected, but then we shift the audio. This shifted version of the audio with the previous subset of frames forms the negative set because here the audio and video are no longer in sync. So this is a very important part of our research. And I want all of you to understand this very clearly. So we can go through it again. So all that we have is a sequence of frames and the corresponding audio. Now we randomly select a subset of these frames and its corresponding audio. And this forms the positive pair because here audio and its corresponding video subset are in sync. This is one thing, that is this formation of positive pair. Now what we do is we have to create negative pairs as well. And how do we get this is using a simple shift operation. We have the audio, we just shift the audio for a few seconds and we get the shifted audio. Now this shifted audio with the previous subset of frames will form the negative pair because here the audio and the video are clearly out of sync. We form k such negative pairs to train our network. Now this form of training where we have a positive pair and negative pair, and then the positive pairs are aimed to be kept close to each other, and the negative pairs are aimed at pushing far away from each other, is known as contrastive learning. So the goal of contrastive representation learning is very simple. It's basically to keep the similar samples close enough to each other, and the dissimilar samples are pushed away from each other. So this is one important thing. Now, another thing to note here is the way we get these negative samples. Here, we are not using any external labels or any kind of manual annotations to get these negative data, but rather we obtain this negative samples from the available data itself, that is from the video and audio itself. And this kind of learning in machine learning is known as self-supervised learning, where there is no need of any external labels to be present, but rather we get all the supervision and labels from the data itself. So here, overall, we set up a self-supervised contrastive learning framework. And this is the major part of how we train our networks. Okay, so this is mainly for the technical audience. I'll try to be very brief about this. Here is an overview of how we of a detailed architecture. So we all know that we have two streams of inputs now. One is the visual stream, another is the audio stream. So for the visual stream, we represent the videos using different types. One is the RGB representation, other is the key point representation, which I'll be talking in some time about how it's extracted. Now, the visual encoder ingests one of these representations and generates the visual features. These visual features act as input to transformer encoder layers, and then we project these features using an MLP layer to obtain final visual embeddings. So this was about the visual side. Now coming to the speech side, we have a speech signal. We first extract MEL spectrogram, and these MEL spectrograms are given as input to the speech encoder, which generates the speech features. And finally, these speech features are projected using an MLP layer to get these speech embeddings. So now that what we have with us is two sets of single vectors from two input streams. One is the visual embeddings and the other is the speech embeddings. So if the audio and the video are in sync, that is, they are the positive pairs, then the scalar product between them should be very, very high. And on the other hand, if they are out of sync, that is for the negative pairs, the scalar product will be low. And this itself forms the core of our network training, that is self-supervised contrastive learning. Okay, I hope that was clear, at least to some extent, of how we train our network. Let us now move on and see the different types of video representations that we use in this work. The first representation that we are using here is RGB frames. So this is a very simple representation. We directly extract the frames from the video, that is the raw RGB frames, and they are given as input to our network. But here, there is one important aspect that we need to note, and that is face masking. So what exactly is this face masking? As I was telling right from the beginning of my talk, the aim of this research is that we should be able to do everything with only gestures, and the model should not look at the faces or use any kind of information from faces or lip movements. Thus, to avoid the model looking at the faces and focus entirely on gestures, we mask out the face region. Now, these masked frames act as input to our network, the visual encoder network, which gives us the visual features. So this was about the first representation. Now, the second representation is key point representation. And in that, we have two subtypes. The first one is key point images. So here, we take the raw RGB frames and extract the key points. Okay, so what are key points? Key points, we can consider them as a representation of different parts of human bodies, like elbows, joints, knees, and so on, which basically help in tracking the motion of these different parts. So we extract these key points and render the extracted key points onto an image to create something like shown in the image there, that is the key point image representation. So this is the second kind of representation that we give as input. Now, the third kind of representation that we use is key point vectors. So here what we do is, we do not render the key points into an image, but directly use the key point vectors, that is the normalized key point vectors, as input to the network. So this was about the three different representations that are used in our work. At this stage, one of the major questions that arises to all of us is, why do we even do all these things? Why do we even consider key point representations? Well, there are multiple reasons to do so. First, key point vector representation is very, very efficient. It is 5.5 times faster than RGB representation. Second, it is very easy to switch between different parts. For example, in our case, as I was talking in the RGB, we need to mask out the face region. Now, in case of key points, it is very easy to switch and to select whichever key points we want. We don't need this additional masking step that is required in RGB. And lastly, using key points directly avoids unnecessary parameters like background, different lighting conditions, clothing, and so on. Thus, due to all these different advantages of key points, we experiment with these three different kinds of representations. And at the end of the presentation, we can see which representation gives which kind of performance. So that was about the representation. Now coming to the loss function that we have used during training. So once we have extracted the embeddings, the visual and the speech embeddings, we use contrastive learning, and we do this using cosine similarity. So the objective here is to maximize this similarity between the synchronized versions of the audio and video. That is, for the positive pair, the similarity is always maximized. And for the negative pair, the similarity is minimized. That is, for all the shifted versions of the audio, we minimize the similarity. So in this way, we train our network using contrastive loss setup. All right, so I think this was the brief of the method. We started with this blocks where we saw these three are the major blocks involved in our method. We had the video encoder, speech encoder, and the synchronization training. And I guess I tried to cover all these three different blocks. And it's clear, at least to some extent, to everyone, how are we training our network. If there are any questions, I'm happy to take it either now or at the end of the talk. So let's move on now to train and test our models. We use publicly available dataset, which is known as lip reading sentences, LRS3 dataset. Basically, LRS3 is a dataset which has more than 400 hours of video data, which are sourced from TED Talks. Now, we evaluate the performance of our network using two tasks. So the first task is the synchronization task, for which we have trained the model. And the second task is who is speaking, or active speaker detection task. And here, for the second task, we do not train or fine-tune the model in any way, but rather just use the synchronization scores to predict the active speaker. Okay, let's now begin into some interesting part, that is looking into our results. So this is the results for the first task, that is the synchronization task. So here, the aim is we want the model to predict by how many frames the video is out of sync with the audio. On the left-hand side, I'll be showing the input video, which will be out of sync. And then we'll use our model to predict the frame offset, that is by how many frames the video is out of sync. And then on the right, we'll be showing the sync corrected video, which is basically the output from our model. Let's start.
Honestly revolutionized my life. Over the next 22 years, my colleagues and I would build the world's and quite honestly revolutionized my life. Over the next 22 years, my colleagues and I would build the world's.
So yeah, I think it was very clear that the left-hand side video was fully out of sync. The video and the audio did not correspond to each other. But now with our model, we were able to determine this frame offset. And using this, we can easily sync correct and obtain the final video output. Let us see some more examples.
Hi, I'm Gabriela Levine. I work as an artist and a technologist, and I build robots. Gabriela Levine. I work as an artist and a technologist, and I build robots.
And here is one more example.
Altro non sono che noi stessi. La fantasia. Altro non sono che noi stessi. La fantasia.
So here in the previous example, it's a very interesting example because the language of the speaker is very different. It's not English. We have trained a model only for English language, but then we can see that our model works on diverse set of inputs irrespective of language, irrespective of speakers, and different resolutions. Okay, so let us see some of the quantitative results from our model. The graph shows the synchronization accuracy that we obtain from our model. The summary of this is that we can see that the RGB representation achieved the best performance compared to other representations. But it is very important to understand the trade-off here. Although RGB gave us the best performance, but we already saw that key points are way more faster and efficient compared to RGB representation. But then if you want to use key points, then it always comes at the cost of performance. Okay, so now let us see some of the results which are out of the data set. So until now, we saw the qualitative results for the data set test set videos. Now we will see some of the results for in the wild real videos taken from YouTube and see if our model can generalize to these inputs as well.
Okay, buddy boy, here it is. You hide my clothes, I'm wearing everything you... Okay, buddy boy, here it is. You hide my clothes, I'm wearing everything you own.
Yeah, so it's very clear that our model is very accurately able to predict the frame offset and sync correct the videos, even if it's completely out of the data set and fully unseen real world video. Here is one last example.
Can I say something? I'm the type of person, if you ask me a question and I don't know the answer, I'm the type of person, if you ask me a question and I don't know the answer, I'm going to tell you that I don't know.
All right, so these were the results for the first task, that is the synchronization task. Let us now see some of the results from the second task, that is identifying who is the speaker in a multi-speaker scenario. So here, I'll be showing the reference video on the top, and the predicted speaker will be shown in green at the bottom.
You're shutting the audience out, but when you're relaxed and open, you're inviting them in.
So yeah, in this particular video, we can see that there were a few instances where the camera angle changed and the speaker's face was no longer visible. Now, in all these cases, the lip synchronization models will not work. They will fail to determine the active speaker because the face is completely not visible. But then, because our model is not using any kind of face information, we can use our model and it can accurately predict the active speaker throughout the video. Here is another example.
To cheer with you two. Neither of you can come to the party.
And here is one more.
It's the beginning of December. So yeah, very clever machine. This is one of our head shells.
Right.
So this was one of the examples that we saw at the beginning of the presentation. So here we can see that the speaker's lips are occluded with a mask. Again, in this case, the lip sync models will not at all work because the lips are not visible at all. But then our model works really well and it's able to predict the active speaker in such cases. So here is one last example.
Like the poor man's version of Ryan Reynolds. And like the rich man's version of my most recent.
So again, this is an extreme example where there's no face, no lips, everything is occluded. So the lip sync models will fail, but our model can work well. Okay, so this was about the results for the two tasks, and we saw that our model is able to decently perform well and is able to predict the speaker from the crowd. Now, we made some more analysis using our model. So before saying what that is, I have a small task for all of you. So I'll be playing some of the videos here without sound, just the videos. And the task is, can you predict the language by only seeing the videos here? Let's start. This is the first video. And this is the second video. Okay. So now I'll be playing the videos with the sound on, and let's see if you can guess.
말 그대로 우리가 누리는 자유는 사회의 법으로 보장되어 있습니다. 많은 사람들은
And this is the second one.
Devono essere analizzati sempre da un punto di vista globale. In tanti progetti che noi vediamo, in tante idee, in tanti articoli vediamo.
Yeah, I think after playing the sound, it's very evident about the languages. The first one is the Korean speaker, and the second video is the Italian speaker. Now, the important thing to notice here is the variation of gestures across different languages. We try to analyze these variations and how the gesture-speech correspondences vary across multiple languages and hence, to some extent, multiple nationalities as well worldwide. We conduct an experiment where we test our model on these different languages and see what it captures and see if there are any specific patterns for each languages that are present. So this is a result. The graph shows the results of our model. And these results are in line with our intuitions and known facts. I think all of us can agree that Italians have always gestured a lot while speaking when compared to other speakers like Korean and Japanese, where they relatively gesture very less. And we also saw these two examples before in the slide. So this is what our model predicts. And using this, we can validate that certain languages like Italian, Spanish, and French have a more explicit and stronger correlation, whereas other languages like Korean and Japanese have weaker links. And because the gestures are more for some languages, our model is also able to capture these relationships very well, and the accuracy is higher. And for the languages where the gestures are less, our model finds it difficult to understand what is happening and capture the correlations. Okay, so to summarize, in this work, we have presented a new task, the task of gesture-speech synchronization, which was not explored before in literature. We devised an architecture and proposed loss functions to train this model. We also provided a detailed analysis of using different input representations like RGB frames and key points. And finally, we demonstrated that it is indeed possible to identify who is speaking using a pre-trained synchronization model, and which just uses plainly gestures and do not rely on any kind of face information, or it does not require a talking head to be available with us. So there are several interesting future directions that can be explored. About the architecture side, we saw that there is an obvious gap between the key points and RGB representation. So bridging this gap would be the next step. And in this current work, we are trying to explore the correlation between gestures and speech. But then exploring the correlation between gestures and language will also be a very interesting future direction that we can look into. So yeah, that was it. Thank you so much. You can visit our website for more information and also read our paper. Thank you. Thank you for listening.
So much. Right. What to do to see the participants?